All right, we're back now, and for part B, we'll just do a quick review what redox reactions are. They're basically reactions that involve changes in oxidation states. That's another way of looking at them. And the changes of oxidation states, of course, are because redox reactions involve transfer of electrons. So if you're moving negative charges around, then of course the oxidation states are going to change. Normally, you'll have an oxidation state for one element go up, and the oxidation state for another element will go down because one is losing electrons and one is gaining electrons. So an oxidation is an increase in the oxidation state because you're losing negative charges, sort of like subtracting a negative in math. And reduction is a decrease, or in other words, a reduction in oxidation state because you're gaining negative charges. Redox reactions can also be other types of reactions at the same time. That's what I said back when we started talking about types of reactions, that there are so many different chemical reactions out there that basically no matter how we classify them, any reasonable classification system will end up with certain reactions qualifying as more than one type at the same time. And so some redox reactions that can also be other types of reactions or classified in other ways would be, for instance, combustion reactions. Anytime you burn something, that's a reaction with oxygen from the air. And reaction with oxygen is one of the definitions of oxidation. And so that is indeed an oxidation reduction reaction. The substance that reacts with the oxygen is being oxidized, and at the same time, the oxygen itself is being reduced. An example of that would be like burning propane. Propane plus 5 O2s from the air will create 3 CO2s and 4 H2Os. And that is an oxidation reduction. You could go through that if you wanted to and find out the oxidation state of each element on each side of the equation. And you would find that one of them is going up and another is going down. In this case, it's the carbon that's being oxidized and the oxygen is being reduced. Corrosion is another type of redox reaction. Corrosion can actually take the form of reaction with oxygen, in which case the equation would essentially be the same as the equation for combustion, only corrosion occurs more slowly. So like, for instance, the corrosion of iron, or rusting, in other words, involves 4 atoms of iron reacting with 3 molecules of oxygen from the air, and you get 2 rust molecules, which are Fe2O3 in their formula. This is actually also known as a synthesis reaction because you've taken smaller, simpler substances, in this case 2 elements, and created a larger, more complicated compound out of them. So when you have 2 or more reactants and 1 product, that's usually considered to be a synthesis also. And in this case, the iron is being oxidized and the oxygen is being reduced. We often think of rusting of a car as being an oxidation, again, because it's the metal, which is the iron is part of, that we basically have to go and get fixed at the body shop and spend big bucks for. The fact that the oxygen from the air is also being reduced is something we don't usually care much about because there's plenty more oxygen where that came from and it's all free. So it's the oxidation we care about, but there is a reduction going on also. Also, synthesis and decomposition reactions. Synthesis, again, is where you have 2 smaller, simpler substances combining to create 1 larger, more complicated substance, like water or like hydrogen and oxygen going to form water. And we've already seen that that's definitely a redox reaction. On the other hand, through a process known as electrolysis, where you basically pump electricity into the water, you can actually break up water into its constituent elements. So you can essentially reverse the reaction above. And the reverse of a synthesis is a decomposition. That's when you have 1 larger, more complicated substance and you break it down into smaller, simpler substances. Okay. Other types of reaction, or another way to classify reactions, is according to what's going on. And one of these types of classifications would be single displacement reactions. We already saw double displacement or metathesis reactions. Single displacement reactions are a similar idea, only they generally involve reaction between an element and a compound. And if the reaction occurs, then the free element will replace one of the elements in the compound. And that would be a single displacement or replacement reaction. Some examples of this would be many metal elements in acids. Like, for instance, if you put magnesium in hydrochloric acid, the magnesium will replace the H plus in the HCl, and you end up with magnesium chloride and hydrogen as a free element. So you start out with magnesium as the free element and hydrogen in the compound. You end up with magnesium in the compound and hydrogen as the free element. So that is a single displacement type reaction. Also, you can get metals replacing other metals in compounds. And so the general rule of thumb is that if the free metal, that is the element that's not in the compound, is more reactive than the metal that's in the compound, then the reaction will occur and the free metal will replace the metal that's in the compound. Like, for example, zinc metal, which I've written a little zero there to remind me that it has zero charge. If you put it in solution with copper chloride, the copper chloride is sort of a pretty blue color, kind of like it looks like Windex. And copper chloride is a soluble ionic compound, so it will actually consist of copper ions in solution and with a charge of +2 because it's CuCl2, and also chloride ions. You can do a net ionic equation for double displacement, or single displacement reactions. Actually, for the one above, so we had, for the one above, we had magnesium metal, which is a solid, in hydrochloric acid, which is aqueous. And of course, in aqueous solution, the hydrochloric acid, being a strong acid, ionizes completely. And the products would be magnesium chloride, which is a soluble ionic compound. So it will actually be present as ions also. And then the other product is hydrogen gas, H2 gas. Okay, so if we look at these things involved in the reaction on either side of the arrow, we see that we have magnesium metal going in, magnesium with zero charge, and we have magnesium aqueous ions with a +2 charge coming out. That's a change. So we would have to keep the magnesium for the net ionic equation. Okay. The two H plus ions come out as an H2 molecule, so they have to stay. Because that's a change. But you'll notice the two Cl minus ions come out as two Cl minus ions. That means they are actually spectator ions. And so our net ionic equation would be magnesium metal plus 2H plus will yield magnesium ions plus hydrogen gas. And again, this is the most universal way of writing the reaction. It tells you that anytime you put magnesium in any acid, it doesn't matter whether it's HCl or HNO3 or H2SO4 or whatever, all acids ionize in water to produce H plus ions. So magnesium in any acid will produce magnesium ions and hydrogen gas. Okay. In the case of this reaction down here, we have zinc as the free metal, so it starts out with a charge of 0. And we have CuCl2, which if you work it out means that the copper has an oxidation state of +2 going in, and chloride, as it always does when it's combined with a metal, has a charge of -1 each. And coming out, you have the free metal copper. So copper now has 0 charge, and the zinc has a charge of +2 because it's in the compound zinc chloride with the formula ZnCl2. And if you work the charge on that out, with the overall charge for the ZnCl2 being 0, and each chloride being -1, as it always is with metals, then the zinc must be +2. So again, we can do an ionic equation for that, where we'd have the zinc solid, as it really is in solution, which is zinc solid. And then we have the copper chloride as ions, because copper 2 chloride is a soluble ionic compound. And then on the product side, we have copper metal, and we have zinc chloride, which means we have zinc ions and 2 chloride ions, because zinc chloride is also a soluble ionic compound. So there's your ionic equation. And you may have noticed so far that the difference between net ionic equations for single displacement reactions and double displacement reactions is that in double displacement reactions, you almost always have 2 spectator ions on each side, whereas in single displacement reactions, you normally only have 1 spectator ion on each side. In this case, it was the chloride, and actually, once again, zinc becomes zinc +2, that's a change. Copper +2 becomes copper 0, that's a change. And 2 Cl minuses remain as 2 Cl minuses. So once again, the chlorides are the spectator ion. And there is your net ionic reaction. And this also makes it quite obvious that it is an oxidation reduction reaction, because zinc goes from an oxidation state of 0 to +2, which means zinc is oxidized. And copper goes from an oxidation state of +2 down to 0, which means copper is reduced. So oxidation reduction. Now back to what I was saying about the reactivity of the elements. The fact that this reaction occurs tells you that zinc must be more reactive as a metal than copper is. And what that means when we're talking about metals, and we're talking about how active or reactive a metal is, well, the more reactive a metal is, the more it wants to do the things that metals normally do. What metals normally do is lose electrons and become cations. And so if zinc is more reactive than copper, then that just means that zinc wants to lose electrons and be a cation more than copper does. Notice the situation we start out with, though, is just the opposite. Zinc is a neutral atom, whereas copper is the cation. They actually want to be the other way around. And so that's what happens. They switch places. Copper, the less reactive metal, is now the free metal, and zinc, the more reactive metal, the one that really, really wants to be a cation, is now a cation, and everybody is happy. And that's essentially why the reaction occurs, because this situation on the right-hand side is more stable than the situation on the left-hand side. The way that you can predict whether a combination of a free element and a compound will react will be by using what's known as the activity series. And don't pay attention to this one because the order is a little different from the normal one. I will post a table in D2L of the activity series that I want you to use for determining whether a reaction like this occurs or not. And what you'll see is that in that, here it is on the computer screen, I will post a PDF of this. And what you'll see is that the elements that are basically the metals that are the most reactive are the ones with the lowest electronegativities. Cesium and francium are right up at the top of the table as the most reactive metals there are. And then, folks, is just getting worse and worse. And then you can go down from there all the way down the list throughout all the metals. And you eventually get to the point where the blue line here is the line between metals that react with acids and metals that don't. So anything that's below this blue line here does not react with most acids. So we have copper here. Copper doesn't react with most acids, and we're getting less and less reactive. And on this list anyway, platinum is the least reactive metal of all. So again, you'd look at the list. If the free metal is above the metal in the compound in the list, then the reaction occurs. Okay. If the free metal is below the metal in the compound, then the reaction doesn't occur. So for the reaction above, the zinc is above or more reactive than copper in the activity series. So if zinc is the free metal and copper is in the compound, that means they're basically backwards from the way they want to be, and the reaction occurs and they switch places. On the other hand, if you were presented with a situation where you had copper metal and zinc in a compound, well, in this case, the more reactive metal is already a cation, which means it's already in the form it wants to be in. And the less reactive metal is the free metal with zero charge, and that's the way the less reactive metal would prefer to be. So they're already happy the way they are, and so there's going to be no reaction. And so using the activity series, you can actually predict whether a combination of a free metal and a compound containing a metal should react or not. Okay, and I will post that activity series on D2L at the same time that I post these lectures. All right, we now move on to balancing redox reactions via half reactions. The 195 over 205 is just the page number in the PDF. It's 195 in the book, but the PDF says it's 205 because the PDF counts all those introductory pages at the beginning that don't have page numbers. So the numbers are actually different by 10. Okay, so the fact is that some redox reactions are difficult to balance by trial and error, which is the way we've been balancing them so far. Fortunately, there is a method that you can use for more difficult cases that will it's a pretty foolproof way to end up with a balanced equation. Essentially, what you do is you separate the oxidation part of the reaction from the reduction part of the reaction. And when you do that, the two halves of the reaction are known as half reactions. So there's an oxidation half reaction and a reduction half reaction. The oxidation half reaction just contains whatever element is being oxidized, including whatever compounds it might happen to be in, and the electrons that are being lost in order to be oxidized. And then the reduction half reaction would include the element that's being reduced along with whatever compounds it happens to be in, and the electrons that it's gaining in order to be reduced. And once you balance the half reactions, then you get it so that the electrons coming and going are the same in the two half reactions. And then you can put the half reactions back together and your overall reaction should be balanced. And the nice thing here is that we can feel free to use water to balance the half reactions. And that's because just about every reaction we encounter in general chemistry occurs in solution, that is in water. And so you can add H2Os to balance hydrogens and oxygens. And many reactions occur in either an acidic or basic environment. And so if it's in an acidic environment, you can use H+ ions to balance out hydrogens, and then H2Os to balance out any oxygen. And if it's in a basic environment, you can use OH- ions to balance out oxygens and hydrogens, and also H2Os, because any aqueous solution has lots of H2Os present. And while the H2Os don't usually get involved in the oxidation reductions themselves, they can participate in the reaction as a source for atoms. And in any environment that's acidic, or an acidic medium, in other words, there will be H+ ions present in addition to the H2Os. If the environment is basic, then there will be OH minus ions present in addition to the H2Os. All right, there are a series of steps that need to be used here in doing this. And so they're written out, they're steps 1 through 8, I believe it is. And if you follow them in order carefully, then you should be okay. So first you have to write the oxidation and reduction half reactions from the overall reaction that you've been given. Each half reaction should contain the reactant compound containing the element that's being oxidized or reduced, and also the product compound containing that element. And so you don't have to take the element out of the compound. If the element is in a compound, you just include the entire compound. Okay. And that might include a different compound on the left side versus the right side, because, of course, chemical reactions often consist of taking compounds apart and rearranging the atoms and putting them back together in different combinations. So the element that's being oxidized or reduced may be in a different compound on the left versus the right. But don't worry about that, just put them both in. And I crossed out part here because I started writing down the instructions according to the way I learned to do it, which is a little bit different from what's written in the book. But as it went on, I decided it made more sense to do it the way that the book presents it, because that's the way all the examples in the book are done. So I went back and sort of changed things so that we're doing it the way the book does it. So say for reduction of chlorine, you can have a chlorine atom going to a chloride ion. Or if you have chlorine molecule going in, that would be Cl2 going to 2 Cl minuses. And that would be your reduction half reaction. And again, we'll go over a couple examples after this, so that won't be the only thing we see. The next step would be to balance all of the elements in the half reactions, except for hydrogen and oxygen, because you're going to use H2Os to balance those later. Okay, then you'd want to balance the oxygens by adding 1 H2O for each oxygen required, and you'd want to add those to the side with fewer oxygens. So if you need 2 more oxygens on the reactant side, you would add 2 H2Os to the reactant side. Then, regardless of what kind of environment it's in, whether it's acidic or basic, either way, you would balance out the excess hydrogens by adding 1 H plus for each extra hydrogen required to whichever side has fewer hydrogens. So if you need, say, 4 more hydrogens on the on the product side, then you would just add 4 H plus to the product side. And then you make sure that you balance the charges between the left and right-hand sides of the two half reactions. The charges don't have to be 0 on either side, but they do have to be the same from the left side to the right-hand side. So balance the charges by adding electrons, and you can only add electrons to balance the charges. And so you'd basically add the appropriate number of electrons to whichever side of the equation has the more positive charge. Okay. And just remember that the reduction half reaction should have electrons as reactants because you're gaining electrons for reduction. And the oxidation half reaction should have electrons as products because you're losing or releasing or giving off electrons in an oxidation. Okay, then you look at the number of electrons involved in the oxidation half reaction versus the reduction half reaction. And if the electrons involved in the two reactions are not equal, you have to make them equal. Because those are the same electrons. The electrons that are taken in for the reduction are the same electrons that are being released in the oxidation. So the numbers coming and going have to be the same because you can't just have electrons appearing out of nowhere or disappearing into thin air. They have to come from someplace and they have to go someplace. Okay, so what you do is you make them equal by multiplying all of the coefficients of the two half reactions by the smallest possible factors in order to get the numbers of electrons coming and going to be the same. It might be that you might have to multiply one of the half reactions by a certain number, and the other half reaction might be okay the way it is. Like if one half reaction has 2 electrons involved in it, and the other half reaction has 1 electron involved in it, well, then obviously all of the coefficients in the equation with 1 electron would have to be doubled, so that now it has 2 electrons, just like the other equation does. Then you would add the balanced half reactions together, and at this point you can often simplify. It's quite common to find H2Os on both sides of the equation, in which case you can cancel out until you run out of H2Os on one side. You can simplify also by, if you have the same item appearing more than once on the same side of the equation, combine them together. You might very well have, say, an H plus and another H plus both on the same side of the equation. Combine those together into 2 H pluses. Okay. Then finally, well, not finally, but almost finally, if the reaction occurs in a basic medium, remember we balanced the hydrogens by adding H plus ions a couple steps back. Well, if it occurs in a basic environment, then you can't have free H pluses floating around, because that's what happens in an acidic environment. And basic is the opposite of that. So what you'd have to do is, for each free H plus on either side of the reaction, you have to add that number of OH minuses to both sides of the reaction. So if you have 3 free H pluses on the left-hand side of the reaction and it's in a basic environment, you're going to have to add 3 OH minuses to that side and the other side also, so that the atoms will still balance. And then anytime you have H pluses and OH minuses on the same side of the equation, they will combine to form H2Os. So if you have 3 H pluses and 3 OH minuses on the same side of the equation, combine those and write it as 3H2O. And now you will have gotten rid of the H pluses on that side of the equation, and you'll have some free OH minuses on the other side of the equation. But that's okay if it's a basic environment. You can have free OH minuses floating around. That's okay. And again, check again to see if you can simplify the reaction. If you have H2Os on both sides of the equations, then you can cancel them out until you run out of H2Os on one side or the other. And finally, check for balance one more time, just to be sure. You want both the atoms and the charge to balance from one side of the equation to the other. And if either one of those doesn't balance, then you got a problem. You did something wrong. Okay, what I tried here as the first example was an example that the book suggested. It was one as part of one of the problems that they actually worked out. Oh, and I see, actually, now that I mentioned, I'm over time on this segment of the video, so we'll actually do the example in the next segment. So I'll see you in a moment.